Hi there. Welcome back to section 2.4, the chain rule. We're going to do our second video here, which again doesn't divide perfectly along these learning objectives, but we will certainly be using the chain rule to find and apply derivatives, so maybe that we'll just pretend it's that second learning objective there. Mostly what we'll be working with is this general power rule. So basically what we're supposed to think of in this case is that instead of having just x to the n, what if we had something more complicated? 2x minus 1 to the some power, 15th, let's say. So the thing we're supposed to be contemplating is something more complicated being raised to the nth power. And how we get rescued by this is with chain rule, essentially. So if you just pretended for the moment that what we really had was just x to the n, then we'd be getting power rule right back again. We'd be having n x to the n minus 1, as usual, pardon the first grade script here. And that would be the end of the story. There would be no times anything else. But this is where chain rule kicks in. If you've got something more complicated than just x down here, just your variable of interest, x in this case, then chain rule basically lets you get away with ignoring the fact that this is far more complicated than just x. It's something much more involved. So, or 2x minus 1, or x squared plus 10, whatever it is that's sitting inside of here, chain rule lets us get away with power rule for the vast majority of this computation. N times stuff to the n minus 1, that's the same as our power rule. The only thing that it actually catches us with, the price that we have to pay, at the very end is that we have to tack on the derivative of the inside stuff. And by inside I mean whatever was getting raised to the nth power originally. And if you note, this is actually still consistent with our original power rule. The derivative of x would just be times 1. So this doesn't actually break our original rule either. It's just that if x was fancier than just plain old x, we'd also have a rule that lets us compute its derivative. So we'll try one out quickly. So 3 over x squared plus 1 all squared. That doesn't initially look like it fits this description. I'll go back to the general power rule for just a second. It doesn't look like stuff to the nth power right off the bat. However, if we remember our rules for exponents, we could rewrite this entire denominator piece as x squared plus 1 to the negative 2. This 3 is still sitting out in front. It was in the numerator, so it's still sitting in the numerator. And then here's what power rule lets us do. Well, power rule and chain rule together. So basically, here's a complicated thing that's kind of annoying me. I realized that if this was just 3x to the negative 2, that basically I could ignore this, that I could just bring this power down and reduce its exponent by 1 and we would be done. And we almost get to do this, surprisingly. The only thing we have to work with is remembering that this stuff inside has to be dealt with by the very end. But the general power rule says, yeah, basically just ignore this stuff in red for the moment. We could just pretend that all this stuff here is plain old x. We know it's not, but in the short run, we're going to get away with it. So we do power rule. The negative 2 comes down, multiplied by what was already out there. So we get negative 6 out in front. Exponents decreased by 1, so down from negative 2 to negative 3. And then it's not till the very end of all that computation that we finally see anything new. So this is the piece that's due to chain rule. So if this stuff in red is u, then this is du dx, the derivative of the inside stuff. And this is where the general power rule kind of links up with the chain rule that we had before. This is the derivative of the outside function, sort of df du, if you will, and then times the leftover bit, du dx, the inside function. So all of our power rule stuff basically gets to sit the way it is, and then we just have to multiply by this derivative by the time we're done. But we know how to do that. Derivative of x squared plus 1 is just 2x. And now we have a rate of change for this relatively complicated thing without doing much new. We just had to calculate one extra derivative that chain rule informed us was necessary. And then with a little bit of simplification, we could put negative 6 and 2x together to get negative 12x on top, and we could drop this all down in the bottom. But this is just fluff. This is icing on the cake. This right up here is a conclusion where all the derivatives have been computed. So that should be fine unless somebody told us simplify your answer for sure. So let's try a word problem with this. So productivity for some product is that. So what we're getting out of this, the productivity in this case is defined as items produced each day, and then W is the number of worker days. So instead of worker hours, we're doing worker days just to make the units a little bit bigger. But well, the numbers smaller but represent larger values. So the thing we're supposed to figure out is at what rate is productivity changing when 5 worker days are dedicated to production. So as usual, we take these words and try to turn them into something mathy. So at what rate is productivity changing? That's going to be our derivative. And then when 5 worker days are dedicated to production, well, okay, so the only catch there is that we're supposed to be getting input, and there's not actually, it seems like we might be concerned about the actual units here, but 5 worker days is exactly what we were given, so we don't have to do any conversion or anything. So when 5 worker days are dedicated to this, it's just telling us that W is equal to 5. So nothing crazy there. So this feels very much like a problem that we would have done in the last couple of sections, 2.3, 2.2, or even 2.1 maybe, until we get to the actual computation. So we need p prime of 5, just making that statement concise. So we'll find the first derivative. And here's the issue. What we've got fits a form, but it looks like some complicated stuff to the 1/2 power. And this is just using the fact that the square root of something is that quantity raised to the 1/2 power. And we see, okay, look, it's in the form stuff to the nth power, which almost looks like power rule, but this isn't quite plain old x. So instead it's this notion, this general power rule, which involves the chain rule. So before this section, we would not have been able to compute the derivative of this thing effectively. Okay, so that's our task. First, find the derivative function, marginal productivity, if you will. So this looks like, okay, we're supposed to treat, just like in that quick example, we're supposed to treat all the stuff inside here as though it were just fixed for the moment, as though it were W in this case. So W to the 1/2 power, its derivative is 1/2 times, sort of ignore that for a sec, power goes down by 1, 1/2 minus 1 is negative 1/2. And then finally chain rule makes us do something interesting. It makes us tack on the derivative of the stuff we were ignoring inside of this. So the reason I keep explicitly identifying the inside part of this is because we need to take the derivative of that boxed quantity before we're done. And then we multiply that to the expression we already had. So chaining it on, if you will, hence the name chain rule. Okay, so this is all done. This is just gonna, have some juice or something while we finish this off. We've got one more derivative to accomplish, but this is just regular old power rule. So 2 comes down, 6W, derivative of 30W is 30. And even if you get overzealous here and you say, well, let's look, what if I hadn't noticed that this was just W? What if I thought it was something more complicated and we did chain rule again? Well, okay, so then we would do power rule as normal. The 2 would come down, and then we'd have to multiply before we were done by the derivative of the inside thing. Well, okay, the inside thing isn't terribly complicated in this case, but it also doesn't spoil our answer at all, because multiplying by the derivative of that per chain rule would just multiply by 1. That doesn't actually change our answer at all. So whether you get kind of tricky with it in either of these cases and think, oh, well, don't I need some chain rule here? It doesn't actually matter in those instances because the derivative of just the variable by itself is going to tack on times 1. That's not actually going to make your answer any different. Okay, so we got our derivative function. We're supposed to plug in a number though. So if we plug in our 5 worker days, we get a surprisingly tidy number, 2. So that's our find piece of this. We're also supposed to, as always, interpret. So coming up with an interpretation for this, when labor is 5 worker days, so that's just the input piece of this, then productivity is increasing. And the increasing part of this is due to the fact that we're talking about P prime. So the original function was productivity. P prime is a rate of change in productivity. And then finally, the actual value we get here. So at a rate of 2, and then the units are always output divided by input. So productivity was units produced every day, and then units on input were worker days. So this derivative is in 2 additional units for every additional worker day we dedicated to production. So it's telling us that perhaps if we went up to 6 from where we are now, then our expected increase in productivity would be a couple units every day. So there's our generalized power rule, and more specifically, or more generally, this is chain rule being implemented in a word problem. But you'll notice that regardless of the strategy we use to get here, the interpretation still follows these typical what does the derivative mean kind of formula. That's it for section 2.4. We'll be back with 2.5 shortly.